All right, so everyone here is going to be paying attention. I don't have any problem with people taking out phones or having earbuds during this, right? So, class.
Yes.
All right, you people. So, you guys sound super amazing, happy, and ready to be here, right? Yay! All right, related rates. This is actually going to be one of those things that. Okay. One of those things that's you're gonna struggle with. Now, I already did this. I already tested this. Now, as we go through and do this, we need to know certain things. Those flashcards. Anyone actually start using those flashcards? Is that a yes?
Yes.
Did you go through it?
I went through it.
Oh, hey, good job. Okay, you might actually get this one. What is the volume of a sphere? Okay, that's going to be one of the things that we're going over because we need to actually do these things. What about surface area of a sphere? These are things that we have to have, that we have to know, that we have to, like, just have here in the back of my brain sitting there waiting for me. So, to solve related rate problem, approach related rate by writing an equation involving time-dependent variables. Time-dependent variables. That means we have to have what variable in every single problem? T. Is there going to be a T in my problems? Mostly not. We have to add that for this. Attained by investigating the geometric and or physical conditions imposed by the problem, we then differentiate the equation with respect to time and obtain a new equation that involves variables and their rates of change with respect to time. Bam. A golfer hits a ball into a pond, still water, causing a circular ripple as shown in the figure. If the radius of the circle increases at a constant rate, okay, now pay close attention. The radius of the circle increases at a constant rate. That's important. How fast is the area of the circle increasing when the radius of the ripple is 2 meters? Now, let's start. Whenever we do these problems, start with what you know. Are we talking about area of a circle? Yes. That means that it's going to be area is equal to pi r squared. What is my radius? 2 meters. Any other information? Right here. It has, the radius has a constant rate. So my radius, so that's going to be my dr dt. That is a rate of change. So my radius here is going to be this, which is going to be 0.5 meters per second. Hey, Tree, remember that cup that you borrowed? Oh, it is? Okay. She said no. Okay. Now, this is important here. So now we're going to use this information to try and solve for this. What am I looking for? That's next. How fast is the area of the circle increasing? So it's area of the circle increasing. So that's the rate of change of the area. So I'm going to have a dA dt is what I'm looking for. going through, listing everything that we have, identifying what it is, and identifying what I'm looking for. That's important. That is key to every single one of these problems. No. Let's see. So now I have area equals pi r squared. Now let's take the derivative of this with respect to time. With respect to time. So that means that this is going to turn into a derivative of a dt with respect to time is equal to, over here, I'm going to take the derivative of this side. My only variable is r, isn't it? So that's going to be a 2 pi r. Am I missing anything? The what? Not time. Did I take the derivative of r? Yes, I did. If you notice that 2's not there, it's out for here, right? Did I take the derivative of something that's not time? Yes, I did. What do I have to add if I'm taking the derivative of something that's not time? There we go. dr dt. That is important, that when we're doing this, this is just like the implicit differentiation. But it's the application now of that implicit differentiation. Do we have the r? Do we have the dr dt? And I'm looking for dA dt. So can I just plug this in now? Yeah.
That's a T.
Where's the what?
That's a T.
T on the bottom, yeah. Sorry, my pen kind of wonkied that one. So this is going to be dA dt is equal to 2 pi, r is 2, dr dt is 0.5. Do the math, I get dA dt is 2 pi. Units. Units is worth 1 point. Okay, 1 point. This problem pops up every year, not this exact, but just like this. Related rates on the AP exam. What are my units? This is always worth 1 point of this to get this right. Say louder, please.
Meters per second?
Close.
No, it's meters squared because it's how fast it is.
So it's area, right?
That's meters squared per second?
Very good. So meters square per second. Yes? That's the rate. Remember that whenever we did this, that's the rate of change, isn't it? So it's a slope, isn't it? Because going back to what the derivative is, that gives me the slope at a point, right? So the slope, dr dt, that's the rate of change of the radius with respect to time. Yes, no, maybe?
Yeah.
Okay. All right. Going on. Yes.
Is meters squared per second different than acceleration?
Yes, acceleration is me driving. Meter squared is an area. So think of acceleration as a
Acceleration is linear, so you just
Yeah,
go
thank
in
you.
one place. So it's just to the power of 1. But area is going in all directions, so it's to the power of 2.
There could be an acceleration on that too if I was asking for the rate of change at the, yeah. So that would be a second derivative. All right, All those things that we just did for that problem is right here. Writing them all down, listing everything. All right, how are we doing over here now? Spherical balloon is inflated at a rate of 10 meters cubed per minute. That is a volume change over time. Find the rate in which the surface area of the balloon is increasing with the radius of the sphere being 3 meters. Now, I have two problems that I'm dealing with here. Volume and area. So volume of the sphere. Volume is 4/3 pi r cubed. Surface area is going to be 4 pi r squared. How many variables do I have here?
In the problem,
Yep, both problems there. How many variables?
1, 2, 2. And it's 10 meters cubed per minute and radius, which is 3 meters.
There's 3.
It's spherical, so we know that it's time.
We're going to have a volume. We're dealing with the volume here. We're dealing with the radius here. And we're dealing with the surface area here, right? Yes? Okay. So what information do I have? I have that my radius is 3. Now, what is that? What is that going to be? What is that going to represent out of my variables? D what? dV. There it is. It's the derivative of my volume over time. So as we're going through, we're looking at this, I have to identify this. So this is going to be my derivative of my volume over time.
So we did a derivative of volume because we're finding the rate of volume. But then why do we do dt?
Okay, so all these problems related rates are respect to what? Time. That's why they're all DTs. Because I'm changing volume over time. Okay? So if I had a dy dx, I'm changing y, right? In respect to x. So that means that as my x changes, the y changes. So it's a slope.
Change the v over change the t.
Yes. So, yeah, it's a slope in between there. So it's actually, yeah, the slope at a point is this right here. Okay, find the rate in which that the surface area of the balloon is increasing. Find the rate that the surface area, so that means what am I looking for in this problem? This one right here, right? The surface area. So I'm just going to call it dA. But the surface area problem, I always write it as SA, surface area. Anyway, but yeah, I'm looking for the derivative of the area with respect to time. So these problems, you have to list them out. This is a puzzle. You put the puzzle together with the clues that you have. So that means I have to go through and do the derivatives of both of those. All right, so I'm going to take the derivative. So it's going to be dv dt is going to be 4 pi r squared dr dt. Where did the 3 go, Anthony?
To the front and then multiply with the 4 over 3.
Very good. Good job. Yep, exactly. All right, so my surface area is going to be dA dt is going to be 8 pi r dr dt. Now, this is a puzzle. I took the first step, I took derivatives. Now what else could I do?
Plug in dr.
Okay, let's start plugging in. Let's plug in now. So, I know what dv dt is, right? And that was what? 10? Okay, so 10 equals 4 pi. Do I know what r is? 3. Okay. 3 squared dr dt. Do I know what dr dt is? No. But by plugging it in over here with the volume, I could do some math and actually get dr dt by itself, right? Because over here, on this side, I'm looking for the dA dt. The only thing I do know is r. I don't know dr dt. Can I do a problem? Can I solve for something if I have 2 variables in it? No, I can't solve for it if I have 2 variables. So what I'm doing is I'm isolating my dr dt over here on the left to figure out what this is. So let's go ahead and plug this in. I'm going to get 10 equals 3 squared is 9 times 4 is 36 pi dr dt. Yeah. So I'm going to get 10 over 36 pi is equal to dr dt. Leave it as a fraction. Don't try and approximate these unless necessary, like you have to because of something. All right, so now I know what dr dt is. So I'm going to go over to the second problem over here. And once I can plug in my r and dr dt, and so that means that I could solve for my dA dt, so my change in surface area over time. So let's see. dA dt is 8 pi r is 3. dr dt is 10 over 36 pi. I wouldn't do that. I would reduce it. Yeah, simplify it. Isn't this right here 24? 24 like that. So try to simplify first before, because if you get into big numbers, you know, it makes your math a whole lot harder. So that's going to be what, 20 over 3? What's going to happen to my pi's? Right? So, for the full credit, my answer is full credit. What is it though? Remember, slightly deaf.
Meters squared per second.
Meters squared per second. Why is it meters squared?
Area and that volume.
It's area, right? Okay, it's area. So he's saying meter squared. Miss Becker, did you have something to go along with that? Per minute. Thank you.
Isn't it asking us to put in the surface area though?
Find the rate in which at the surface area. So the rate of the surface area is what I'm looking for there.
What was the simplified?
What is the what?
What was the simplified?
I'm putting it back so you guys see it. There we go. So we are right here.
That's what
Other questions, concerns, complaints, conspiracy theories? Now, before we can get to this one right here, we're going to stop right here. We're going to pick up this one here tomorrow. What else are you guys picking up here today?